Hello everybody. Today we will cover a quite often misunderstood concept in physics, and that concept is electric potential or voltage or potential difference or electric potential difference or electromotive force. There are a lot of names for it, and I have found that a lot of books and scientists and engineers are not very consistent with their usage of what term they're using. Technically, different terms have slightly different meanings for really what kind of thing you're talking about dealing with it, which we'll come up to later. For this one, I'm going to try and mostly stick to saying electric potential or voltage. Those are the most often used ones. And again, there's not a lot of consistency in usage between scientists, and even just along one scientist using it a bunch of different ways. So you kind of get used to that. Sorry. So for this, we're going to use one of my favorite analogies to understand the basic idea of what voltage values are telling you. I will do my best to leave out the math. I think I have one equation in here because this is simply intended to give a conceptual idea and a conceptual understanding of what voltage is trying to tell you. We will use other analogies later to give more detailed understanding of what exactly you can get from voltage. This is just kind of our introductory understanding of it. Okay, so what is this thing? Well, first off, it allows us to make electrical things work and complete different tasks. This is lighting in your house, your cell phones, TVs, your car, all kinds of things run on electricity, and we use it quite a lot. We can use it even specifically these voltages to compute information with a computer. I think that's too many computes. But anyway, the basic idea is that electric potential / voltage is the potential to move a charge or the potential energy per charge. So I'm going to repeat that. It's the potential to move a charge or the potential energy per charge. Okay, so let's get into our analogy. So for this situation, we need a strong man, and let's call him Schwain the Stone Schmonson. Well, that's hard to say. Or just the Stone for short. We'll go with that. We also need a weak man. Let's call him Schmanny Schmavito. And again, that's tough, so we'll go with Schmanny for short. And we're going to put them into a situation and try and figure out, what would happen here. So there their names come up. I forgot to have those come up. My mistake. But anyway, the Stone and Schmanny. So we're going to put them each in a situation where they are alone in a room. And the question is, who is lifting more weight? All right? And it may seem obvious to you, the answer here, but, we're doing strong versus weak here. It seems like, the Stone is way bigger, he's way stronger, but we have to think about something. We have to think about the available weights. And so who is lifting more weights? The answer to that is, it's Schmanny. I kind of forgot to tell you a little part about the weights that they had available actually to lift. It turns out that Schmanny is in a room that has a small little barbell, a little dumbbell that he can pick up, and the Stone unfortunately has nothing there to lift, and so he is sad. But just remember, my original question wasn't who can lift more weight, but rather who is lifting more weight. If we ask who can lift more weight, the answer is going to be the Stone. He's much stronger, he's bigger, and so he has a greater potential to lift weight than Schmanny does. All right, but he can only do it if that weight is available for him to lift. All right, so in a similar fashion, electric potential tells us kind of the same thing. It doesn't really tell us how much electric charge or current or anything is being moved, but rather how much could be moved if it is available to be moved. All right, so I'm going to say that one more time. Electric voltage doesn't tell us how much electricity or charge or current is actually being moved. It only tells us how much could be moved if it was available. Okay? And that's a very important idea behind voltage. Voltage is more like the who can lift more weight rather than who is lifting more weight. Okay? So in this idea with voltage, we can have high voltages, we can have low voltages, we can have high currents, we can have low currents, which is the moving charges as we know from class. And yes, I realize these are relative terms, high and low and things like that. So kind of relatively high and relatively low, but stick with me here. High voltage does not necessarily mean a low current. All right, high voltage means that you have the greater potential to move a high current. And low voltage does not necessarily mean a low current. All right, it's not a given. You have to look at also what's available. Okay, so give a couple of examples here. Stun guns. Stun guns are used for self-defense. They're supposed to be non-lethal. I think there are times when people have pacemakers that doesn't work out quite as well, but for the most part, they are non-lethal, and they are designed to be that way. If you go look at stun guns and you're ever looking at them or anything like that, you'll see them. They'll have things like 30,000 volts, 50,000 volts, 100,000 volts. I mean, huge voltages, huge electric potentials, but they're still non-lethal. And the reason they are is because these are what are called current-regulated devices. They have a very high voltage, but a very low and regulated amount of current available to them to move. We'll get into later how we can do this current regulation when we start talking more about power. But for now, just trust me, they have a lot of ability to move charge, but they don't have a lot of charge available. And the reason they want this is because current is what is deadly. Current going across your heart can stop your heart, and it can kill you. Whereas voltage, it kind of hurts, and it can push the electricity through you really fast, but it's not what kills you. So with a stun gun, you want something with a very high voltage and a very low current. You don't want it to kill them, so you want low current. You want high voltage or high electric potential because if they're wearing a thick jacket or something like that, you still want to be able to shock them and get them to leave you alone without causing any permanent or lethal damage. On the other hand, we have power lines. All right, power lines are also a high voltage, low current situation. And here we have to really put low current in quotes here because this low current can still kill you. Okay, so one of the things they do with electric power lines is they actually limit how much electricity they send along the line, and rather what they send you is the high voltage. All right, current going through things, all those electrons, they create a lot of heat and it's a lot of wasted energy. Whereas here, if we just send voltage, it's basically like sending just the electric field. There's not really a lot of heat created. Now again, when I say not a lot of heat, there's still a lot of heat. It's just low compared to what it was when the electricity was created. And when I say low current, I mean low compared to when they first made the electricity. It's still way more than enough current to kill you if you start touching them and messing around with them. So that's a low current there. Then when this gets to your house, or just before it gets to your house, it goes through what's called a transformer that actually drops the voltage down to a lower voltage and ramps the current up. And here we have a high current, we have the ability to have a high current along with then in your house a low voltage. So if you look at, say, a wall outlet and you plug something into it, that's getting 120 volts, which is way less than the 30, 50, 100,000 volts of a stun gun, but that actually can kill you and it can really hurt you. And if you go inside the actual breaker box, which I don't recommend you doing, you'd actually find a 240 volt difference there, which is really enough to give you a good jolt and really seriously hurt you or kill you. So even though those 120 volts and 240 volts are way less than the stun gun, they are way more lethal because there's a lot more current available coming from the power station to be pushed through you and do some damage. All right, so keep in mind though, with that, high voltage and high current equals danger. And most often, they don't say high voltage or high current. They usually just say high voltage, because a lot of times high voltage means there is that potential for a very high current and it's very dangerous. So always, and I put it here, I wrote the whole thing out, always heed high voltage warnings. High voltage often comes with high current and is very dangerous. And remember, it's current that kills. So be very careful around high voltage. Don't just think, oh, Professor Allman said that high voltage doesn't mean high current and current's what kills, so it's safe. No, not telling you that. Usually high voltage means stay away, because a lot of times it is accompanied by a high current. Okay, so some key takeaways we need to remember here is that voltage doesn't kill you. It's the current or the charge that is often associated with it that does the damage and can kill you. Current is the thing you really most have to look out for. It's what can stop your heart. Low voltages can still provide a lethal current, so don't think, oh, it's only 100 volts, I'm fine, or it's only 12 volts, I'm fine. It can still do some damage to you. Typically, though, the most common devices are what are called ohmic devices. They follow what is called Ohm's law, that V equals IR there, and there it's also pictured for you, even though I think my face is covering up the V, but that horizontal axis is the voltage. And as voltage goes up, current goes up directly proportional with it. So again, usually high voltage means high current, or at least very often it does. And that's the only equation that I had planned here or to show y'all. So just that simple one, V equals IR. So in conclusion, hopefully you have a better understanding of what electric potential or voltage is telling you, and some of the applications that go along with this understanding, since I gave you a couple of them. So that's about it for this video. I hope you take care, and I will see y'all in class soon.